Hi, welcome to CEE222 Week 11 Recitation. So let's get started with this first problem. So this question asks us to continue this problem 6.9 to solve the water depths at these four different locations: 188, 423, and 748, and the final one, 1,675 upstream of the dam. And the question asks us to solve with the standard step method. Okay, so I think Ethan have demonstrated this problem in the class using the Excel. So I will just use the same Excel to explain how can we solve these. Okay, so this is a Excel sheet that you can download from the course site. So open with this sheet, you can see the diagram of this problem. So we try to solve this water profile upstream of this dam here, and we already know the water depths at this first two location, which is this 188 and 423, because the problem, the question tells us we already know the value for these two locations, and we want to solve the other two, which is 748 and 1,675. And this first sheet is the standard step method equation sheet. So Ethan have labeled all these equation for you to solve all these 13 terms. Okay, so I think I'm not going to repeat all this procedure again, because I think you should have learned this in the class. So here I will show you how to utilize this Excel sheet to solve this problem. Okay, so let's start with the first demonstration. So let's first verify the first point, because we already know the answer for this point through the textbook, and the answer at this point is 1.91 meter for this water depth. Okay, so let's first verify whether that is correct and whether we can really use these Excel sheets to solve this numbered out. Okay, so let me switch to the next one. So here just the basic information that you will got from the problem, and you can put down at here these yellow background color cells in Excel. Then, because we know the distance, the delta L is equal to 188, so you put the 188 at this box. And this section 1 and section 2, this section 1 is referred to the point at this y equal to 2 area, which is the initial, the starting point of our calculation is at the downstream area, okay? And we want to solve this one, the section 2, which is the point at here, okay? The delta L equal to 188, the upstream area here. Okay, so we put down the control sections water depth, which is equal to 2 meter, y equal to 2 at here, right? And the z is equal to 0, because this is our control point, so we set our data at this point, so the z is equal to 0. And the rest of the cell, you can see there's equation here, and you can follow these to calculate all those terms. So I'm not going to repeat why we have those equations here. You just need to follow this equation, and you can solve the rest of the term for this for this column. Okay, then we want to solve this one. So the information that we know is this delta L, and we try to solve these the water depths at this location. So let me circle this. So here is the term we try to solve, and we can calculate the z at this point because we know that we know the slope here and we know the distance. So so we can calculate this z by times this s naught with this distance 188. So that's equal to 0.188 that I show here. So this is the box that you need to modify. Then we start our try and error procedure because we try to make this energy balance with the correct water depth. Okay, so the answer tells us, I mean, in the textbook, the example tells us that the water depth at this location is equal to 1.91 meter. And if we put this number down, we found, okay, these two energies are really close to each other. So we believe that this water depth is okay for this, is acceptable at this section. Okay, and just to demonstrate, let me change to a different number and we will see the difference. So let's see if I put 1.8, then we see the value here is not matched to each other. And the job you need to do is to try and error and try to find out the number that can make this H, the energy, close to each other at this two section. Okay, so we have verified that we can use this equation, use this Excel sheet to solve the water depth. So given that we already know this section 2 and section 3 that I show on this figure here, we want to calculate the section 4 and section 5. Okay, so let's go back to here. Now let's jump to the section 4. We want to calculate this 1.74, even though I show the answer here, but I just want to that you have the idea of what we are doing right now. So again, now the delta L, because we start from this section 3 to section 4, so delta L is 748 minus 423. So that's equal to 325 here. So you need to put this number down. And the other thing that you need to modify before you start trying error process is this delta Z. Okay, so similarly, you can just this for section 3, you just times the 423 to this 0.001, which is 0.423. And similarly for the section 4, which is the section that we try to calculate is 0.748. Okay, and after doing that, we can start the try and error process. So because the water depth is decreasing, so we just get a number that is smaller than the previous section. So try 1.7, well, is kind of close to each other, and we just need to adjust it a little bit. Then we find the number that make this energy at these two sections are balanced with each other. So we take this water depth that we calculate through a try and error process to our problem. Okay. So let's go back to this table. Now we use the Excel to solve this, And you can use this section 4 to further solve this section 5. Use the same method that you input the corresponding z value at this column 4, and you try a different number for the section 5 here, and you try to balance this h with this section 4 and section 5, which is here and here. Then you will find this 1.66 that make the total energy at these two sections are equal to each other. Okay, so the second part of the question is asking us whether the normal depth has been reached in the last cruciation. So essentially, we want to check whether this 1.66 is the normal depth or not. So I think Professor Yang also showed the calculation for the normal depth in the classes to you, but here I just repeat it again just to make sure you know how to solve this. So you can find the rest of the calculation for the normal depth in the textbook on page 228. Okay, so here we will use the graphic method to solve the normal depth, which is the figure 6.4a in the textbook. Okay, so first we need to calculate this term. I just going to write this equation down for you. Okay, and we just fill in the numbers that give by this example. So here is the n is equal to 0.025 times the flow rate 12.5 divided by km, which is 1, and the slope 0.001 to the power of 1/2 times the width of the channel 4 to the power of 8/3. Okay, then we get this number is equal to 0.245. Next, we can go back to the figure 6.4 and using the n value equal to 1, that we can get this yn over b turns equal to 0.415. That means the normal depth that we want to solve is 0.415 times b. Okay, and b is equal to 0.415. Then we have our normal depth equal to 1.66 meter. So in this case, we can show that at this section 5, the water depth has already reached the normal depth. Okay, so we have solved this problem. So essentially, in order to solve it, you need to know how to use this table showing the Excel sheet. And for all those terms, you should be familiar with what equations they use to calculate each cell. Okay, but I leave that work on you. If you have any question about this procedure, you can ask me during the recitation section in person. Okay, so let's go to the next problem. So in this problem, it's really similar to the previous one. However, this time we are using the standard step method. To solve the location given the water depth in the cross section. So it's actually sorry, my bad. So in this problem, we are using, oh, how can I erase this? Using the direct step method to solve the distance given the water depths at different section in this along this channel, and we want to compare the result with the results that we solve using the standard step method. Okay, so the procedure is quite similar to the previous one. So if you open up the Excel that you download from the course site, you can find the sheet labeled with this direct step method. So it's really similar to the standard step method. Okay. So again, you need to fill out, because now it's given the water depths at different locations. So you need to fill out this Y and try arrow on this delta L to see whether that satisfied the requirement. But this time, it's because we already, this is called the direct method, so we don't really need to go through the try and error process. If you fill in all those cells number with these corresponding equations as I show on the screen, I just pop this out, then you can calculate this delta L using this equation down here. Delta L is equal to ED minus EU over the slope minus the average of energy line, slope of the energy line. Okay, so then you can solve this 186 for distance between the section 1 and section 2. Okay, so that's fairly straightforward by using this Excel sheet. So here, I'm not going to repeat for all those procedure for these 5 sections, but I show the answer here. So now you input the different value. How can I write this? Okay, you input these different Y value as different cross section. Then you can follow the equation shown in Excel to calculate the rate of return, and you got the delta L for different section. And you just accumulate those delta L together, then you can get the absolute solution location for those 5 section given those water depth. So let's do a simple comparison. Here is the theoretical value that given by the problem. So here, the first section should be 188, 423, 748, and 1675. Okay, so we can see that the value we solve using this direct step method is quite close to the actual number, or the number that we use in the standard step method. So we can conclude that the answer solved by the standard step method and the direct step method yield a very similar result. Okay. Okay, so in this problem, we are given a 10-meter wide rectangular channel to carry this amount of the water flow. And in diagram down here, we have the dam at this location to raise the rise the water to let's say not at this point. So to rise the water to 5.7 meter at the location 5 meter upstream from the dam. So let's say we have a 5 meter distance here, and we try to rise the water to 5.7 meter at this location. Okay, so we want to first to determine the channel and flow classification, whether it's M2 or X1, and we need to calculate the water surface profile upstream from this cross section. Okay, and at this location 200, 600, 1500 and 3000 meter upstream. Okay, so this is the second thing that we need to do. So let's start with the first one. So here, the first one, which is the flow classification, and we need to first identify whether this flow is supercritical flow or subcritical flow. And to do that, we will compare the normal depth and the critical depth for this channel. And these two information have been given by the problem, which is here. So we have, let me just write here. The normal depth yn is equal to 0.78 meter, and the critical depth yc is equal to 0.639 meter. And we found that the normal depth is larger than the critical depth, and this tells us that this flow is subcritical flow. So the channel is a mild channel that have a subcritical flow if you want to be specific. So let's just write down mild here. So this will be the M curve. Okay, so whether it's M1, M2, or M3, let's further analyze that. And to do that, we know that we have water depth equal to 5.7 meter at our control section. And let me just call this Y plumb. Okay, so this Y plumb is larger than the normal depth yn. Okay, so that's just recall those curves from either Ethan's slide or the textbook at page 223. We can see that we have three different N curves here, and because we know that the water depth at our control section is larger than the normal depth, and among these three different flow curves, only M1 can result in the water depth that is higher than the normal depth. Okay, so it's this M1 curve. Okay, so let me move this away and go back to the problem. So now we know that this is M1, and let me draw an illustration here. So this is YC, this is YN, this is data, and the flow is look like this. Okay, this is a bit over exaggerated, but I just want to show you how this N1 curve look like. So if we go further upstream, so this is downstream area, this is upstream area. Okay, we know that the water depth is decreasing. Okay, if we go further upstream. And we will use this concept to solve the water profile for this M1 curve. Okay, so let's go back to the problem again. So the problem gives us the distance of those sections that we want to calculate the water depth. So that's tells us we should use the standard step method to calculate that. So you can pull out the Excel again and follow the procedure of the first problem that we show in this recitation to go through the trial and error process and to calculate the water depth using the Excel sheet provided on the course site. So here, I just show you the results. The only thing that you need to modify, only two things that you need to modify is this z, because you need to calculate the elevation by using the slope and the distance. So z equal to is not times the distance L. Okay, and because here we have a rectangular channel, so the area here should change to B, which is width of this channel, times Y. Okay, so you need to modify this area in Excel in order to calculate all this number. Okay, for the rest of the term, should remain the same, that you can just follow the step in the Excel, then you can calculate the number. But just remember that this is delta L. So the delta L for the first section is equal to 200. Delta L for the second section, because it starts from the previous section, so you need to subtract these two numbers, which is equal to 400. 600 divided minus 200 is equal to 400 meters. That's why you have the 400 delta L here. So similarly, you can use that to calculate the rest of the section. And here is what you will get if you do the trial and error process yourself. And just to remind you, the criteria for this trial and error process is this total energy. You should try to find a number that make the total energy of this upstream and downstream section to be close at each other. Okay, so that is how you solve it. Now, let's move on to the next problem. Problem 8.9.3. So in this problem, we want to determine the flow rate Q given this problem setting. That we have the square area of this concrete culvert, 6.5 feet times 6.5 feet. Okay, and the head water is 13.3, which is higher than the culvert. Okay, and we have the distance of this culvert and also we have the slope information that equal to 1%. So the problem asks us to assume that the outlet is not submerged, which is in our category is category C. Okay, and to find the flow rate and to verify that the flow rate that we found is not the category B. Okay, so what is category B and C? Just quickly recall that the case B have the outlet water flow is equal to the normal depth, and for the case C, the pipe is partially full. Okay, so it's indicated in this diagram. I think you can quickly recall what Ethan have told in the lecture. So we will use this concept to solve this problem. So let's start with assuming we are in the case C, and in the case C, the flow rate can be calculated using this equation. Okay, and this H here, the H here is the depth above culvert center. Okay, and because this is a concrete culvert, so CD is equal to 0.6. So we here no. Yeah. This CD is an empirical coefficient, and for the square-edged entrance, we usually use the value 0.6. Okay, so it's not because of the concrete culvert, it's because of the shapeless culvert. So here we use 0.6 times the area, which is 6.5 square, because this is a square culvert. Okay, then we just plug in the rest of the number, 2 times G, which is 32.2, times the H. You need to calculate the average, the depth above the culvert center. So it's 13.3 minus 6.5 divided by 2, and the entire term to the power of 1/2. Then you can get that the Q is equal to 645 CFS. Okay, so after we know the flow rates, we now need to verify these flow rates can actually fit to our assumption, which is in the case C instead of case B. To do that, we need to check the normal depth to see if the pipe will flow full or not. To calculate the YN, the normal depth, we'll use the graphic method. So you need to first calculate this term. This is equal to 0.013 for the concrete times 645 divided by Kn times the slope is 1%, so it's 0.01 to the power of 1/2 times b, the width of the channel or the pipe, and in this case it's 6.5 feet to the power of 8/3. Okay, so you can get that this number is 0.38. And then you can use the figure 6.4 as we did before to get this term. The normal depth of B is equal to 0.8, and then you can calculate the normal depth that is equal to 6.5, which is this B times 0.8, equal to 5.2 feet. So let's check the normal depth and the opening of the culvert. So we show that this normal depth yn is equal to 5.2 feet is less than 6.5 meter, which is the height. How does let's just draw this curve out. This height 6.5 meter. So we verify that the flow in this procedure, in this profile. So here will be the normal depth, and here is the opening 6.5 meter. So we can conclude that this satisfies our assumption that this is indeed in case C. So the flow rate that we calculate is correct, which is 645 CFAs. Okay, so I stop here for 2 seconds for you to read through this calculation. Okay, so now let's look at the problem 8.9.4. So in this problem, the city engineer is concerned about damage to homes upstream of a box culvert during the 100-year flood event, which the flow rate for the 100-year flood event is equal to 12.5 cubic meter per second. And we also have a square concrete culvert for this problem, with the length of the culvert is equal to 15 meter, with the bottom slope of 2%. And from the backwater computation, we know that the tailwater depth is equal to 2.75 meter above the invert of the box culvert during this flood event. And we also been given the information that if the upstream water depth, let's call this YU, of 3 meter, then the flood will begin. Okay, so the problem asks us whether the homes is in danger of this flooding event. I mean the 100-year flooding event, and we want to determine the velocity of the flow through these culverts as well. So because we already been told the tailwater depth is 2.75, and these two let's call this tailwater depth YD, is equal to 2.75. And this YD is larger than the height of the culvert, which is equal to 2 meters. So we know if we follow those four categories, this is the case A. That this, okay, this is a bad drawing. Like this. Okay, so both the inlet and the outlet of these culverts are submerged under the water, so we can consider this as a pipe flow. Okay, so if we know this problem is in the case A, then we can use the following equation to calculate the height of this upstream area. So to do that, we will write down the equations to solve these head loads, because we want to use the energy balance equation to solve this height. Okay, so in order to okay, let me just write down the energy equation first. So this YU plus the elevation change due to the slope in the culvert will equal to 2.75 plus the halos. Okay, so this is Z essentially. Sorry, it's better. Z, and this is YD. Okay, and we set the data at the downstream area to be 0. So that means we actually add a 0 here. This is Z down. This is Z up. Okay. So we know this is the YU is the variable that we try to solve, and we know the slope, we know the length, and we want to calculate these halos. Halos have the equation shown here. Times 2G plus 1 Q squared divided by 2G dot A squared. Okay, and this RH is the weighted perimeter. So, oh, no, it's not a weighted perimeter, it's the hydraulic radius. So this is equal to A divided by P. That's this A is 4, because this is a 2 by 2 square edged culvert. So 2 times 2 is 4. Divided by the weighted perimeter, which is 2 times 4. That is 8. So this is 0.5. Okay. So let's plug in all the value together to calculate the halos. KE, the entrance halos, is equal to 0.5 plus 0.013 squared. This is the Manning's coefficient for concrete. Then we times 15, because the length, the L, is equal to 15. And we just calculate this. Radius is equal to 0.5, and we need to have the power of 4 over 3 times 2G. 2 times 9.81 plus 1. And we will times this entire term with the flow rate, 12.5 because these flood events have the flow rate equal to 12.5 cubic meter per second. Divide by 2G, 2 times 9.81 times the square of the area, which is 4 to the power of 2. Then we can get the answer is equal to 0.81 meter. So we calculate the halos, then we plug these halos back into this equation. And let me rewrite it here. Yu, the value we're trying to solve, plus this term equal to 2.75 plus the halos, and the halos here is 0.81, and this term, let me write here, SO times L is equal to 0.02 because we know that the slope is equal to 2% and the length of the culvert is 15 meters. So we know this term is equal to 0.3. So you plug in here, you can solve the Yu is equal to 2.75 plus 0.81 minus 0.3. That is 3.26 meters. Okay, so we solve the water depth at the upstream area. So the next question is whether this flood event will cause the damage in the upstream area. The question tells us if the water depth is higher than 3 meters, then it will begin to flood the homes. So this number is larger than 3, so it will danger the homes. Okay, so because we already know the flow rate is equal to 12.5 cms, so we can easily calculate the velocity. That is equal to Q divided by A, that is 12.5 divided by 4 is equal to 3.13 meter per second. Okay, so we also have the velocity that is required by the problem here. So let me just stop here for 2 seconds. Okay, then we can move on to the next problem. In this last problem, the problem 8.9.7, we want to determine the size of the circular corrugated metal culvert that will fulfill this design condition shown below, which is a 2 feet length with 0.1 slope and a flow of 88.2 cubic feet per second. And the problem tells us the outlet will be unsubmerged, but the inlet is a square edged will be submerged with a headwater depth of 6.6 feet above the culvert's invert. So this actually tells us we want to design the culvert in case B or C. B is for full pipe and C is partially full. Okay, so we need to calculate the size under these two different cases. So let's start with the case B. And just for notations, because this is a circular pipe, circular cover, so we say the diameter of these circular covers is denoted as this D. Okay. So for the case B, we'll just we need to use the energy balancing equation and calculate the halos and solve the corresponding D, the diameter of the circular pipe, given this to satisfy the given condition. Okay, so let's start with writing down the energy balance equation out, which the upstream water depth, the U, YU, okay, plus S naught times L equal to D plus HL. And if we plug the number in, the Y upstream given by the problem is 6.6 feet plus 0.1 times 200 equal to D plus HL. And HL will equal to 26.6 minus D. If you reorganize this equation, you can get this one. Okay, and the other equation that we know for calculating the head loads is this: KE plus Earn square L divided by 2.22 D4 times 2G plus 1. So this is the same equation that we used in the previous problem, but you just need to fill in the corresponding number to get this. Okay, so again, we plug in the corresponding number. The entrance halos coefficient is 0.5 plus 0.024. This is for the Manning's coefficient. The square times the length is equal to 200 feet divided by 2.22 D4 4.0 to the power of 4 over 3 plus times 2 plus 1 times 8, and we know the flow rate is equal to 88.2 square divided by pi squared. G is equal to 32.2 times D to the power of 4. Okay, so now you have these two equations, and you can use these two halos expression to solve for the unknown variable D, the diameter, which is the size of the circular pipe. And this gives us this following equation if you merge these two expressions together. That's 26.6 minus D equal to 1.5 plus 21.2 divided by D to the power of 4 over 3 times 196 divided by D to the power of 4, and we can solve that diameter is equal to 2.75 feet in this case B. Okay. And if we are in the case C, okay, then the calculation is more straightforward. We will use the equation this. Okay, so we have also shown this example for case C in previous problem. Here we would follow the same step, and the h here is the distance to the center of the culvert, so we need to minus d divided by 2. So we will get this equation that the flow rate is equal to 88.2 times the coefficient CD, and for the squared aged culvert, this CD is often to be set as 0.6. The area, because it's a circular culvert, we have the equation for the circular area here. Then we times 2 times G is 32.2 times H, which is 66 minus D over 2. This entire term to the power of 1 over 2. Then we can calculate that D in this case C will equal to 3.25 feet. Okay, so let's just quickly review the calculation that we show here. Here from the problem, we identify that this problem is either in case B or case C. And we follow the equation procedure that we show in previous problem, then we can solve the corresponding size, the diameter for this circular culvert. And for the case B, you have to strictly fit this size in order to get this to satisfy this certain condition. But for the case C, we can choose any standard pipe size that have the diameter larger than this D. Then the flow rate, the flow condition can be satisfied. That for the partially full pipe. Okay, so in this case, because we usually want to choose a predefined or the standard pipe size, so I would argue that this case is a more likely situation to happen. So in that case, we are more likely to use this criteria for our design. Okay, so this is the end of this recitation for this week. See you.